In this video, we're going to focus on the properties of gases, and we're going to go take a look at a theory that we use to explain properties of gases, and that theory is called the kinetic molecular theory. So let's go ahead and take a look at our slide deck over here, and then we'll go to our handout and do some practice problems and elaborate more on some points said within. There's a great video here that goes over particle motion for gases and their properties. So do watch that video to get more details. But essentially, as you know, for the most part, for the gas state, is that the gases take up the shape of their container. So they have variable shapes. They take up the volume of their container. They have variable volumes. They're highly compressible, so you can kind of squish them into a more compact space because there's so much space between them already. You can bring them closer together, and that's essentially because they have very low density. They flow very easily, so that means they have a low viscosity. High viscosity means like it flows slowly. For example, molasses or ketchup or anything sort of like a thick sauce that flows slowly is more viscous. Gases, because there's so much space between the particles, they're miscible with each other, which essentially means that they can mix with other gases. That's what miscible means. And then random movement. Remember, we saw gases have that vibrational, rotational, but also translational as they vibrate and rotate too. So they have this interesting random motion to their particles. And that's called Brownian motion. There's more details on that, so you can watch that video to see Brownian motion if you want more details and are interested. And then the other thing about gases as well, we'll learn in more detail later on, is that when you increase the temperature of a gas sample, the gas expands because the particles move farther away from each other. So let's go take a look at what theory we use to talk about gases. We talked about particle theory to explain behavior of matter as you go from solid to liquid to gas, and the other way around as well. And that works for the most part. When we study the science of gases in more detail, we invoke or use another theory called the kinetic molecular theory, KMT. And so the kinetic molecular theory is a theory that's used to explain the behavior of gases as if they're ideal gases. So I'm going to go to the next slide to explain what an ideal gas is quickly. And then we'll come back here and take a look at the main points of the kinetic molecular theory. There's 5 main assumptions for the kinetic molecular theory. So I said that the kinetic molecular theory really helps to explain an ideal gas. So what is an ideal gas? It's a hypothetical gas that does not exist in our environment. Okay, it's hypothetical. So the gases that do exist, that we do study, they're not really ideal. Okay, they're real gases, but they do follow the rules of kinetic molecular theory anyways. So the ideal gas is described by the kinetic molecular theory. There's no such thing as an ideal gas, but for the most part, our gases are close enough to being ideal, and it makes our calculations and understanding of them easier if we pretend like they are ideal. Okay, so essentially, that what makes a gas ideal is that the particles will have a mass but no volume, and there's also no forces of attraction between the particles, which is weird. The particle theory said all particles have attraction between them. But when it comes to gas, that attraction is so small that we, in kinetic molecular theory, we just assume it's not there. So let me go over that again with our points. So kinetic molecular theory is a way to explain gases. And when we explain gases, we think of them as ideal gases. That's not really how they behave, but for the most part, they're so close to being ideal in regular sort of experiments that we do in everyday life that is close enough. And so there's 5 main assumptions for these ideal gases under the kinetic molecular theory. Firstly, gases move randomly in a straight line. So they'll move randomly, and they'll go from here to here to here to here to here. So they'll move randomly in a straight line. Second point is that the volume of gases is negligible. They're point gases. So what we're basically saying is that the individual particles of gases have no volume. They don't take up space. Even though they technically do, they're so small, there's so little space in between particles of gases anyways, that we say their volume is negligible and doesn't really count. And that makes our calculations easier as well. So we call them point masses, anyway, which essentially means that they're little particles with masses but no volume. In reality, they do have a volume, but it's so small we don't really consider it. Now, the other thing that we say under the kinetic molecular theory is that the gas molecules do not attract each other. So particles of gas won't be attracted to each other, and they won't be repelled by each other either. In reality, all particles are attracted to each other in some way, shape, or form, but gas particles have so much energy, they're moving around so fast that that attraction is negligible. Again, negligible means like so small we can kind of ignore it. And so that's important too because it makes our calculations and assumptions and explanations a little bit easier. So even though there is some attraction, under the kinetic molecular theory, we're going to say there is no attraction if it's an ideal gas, and it's close enough to how gases behave. The other point that's a little bit different that you haven't really heard of yet, or may not have heard of yet, is that if the gas molecules or particles collide with each other, then the total kinetic energy will stay the same. And we call that elastic collision. So think of it this way. If you have a ball and you drop it, it's going to hit the ground. It's not going to bounce to the same height that it did before. It'll bounce lower and lower and lower and lower until it stops bouncing because you have a transfer of energy happening. Now, that's what typically happens to objects and particles. Now, for gases, even if they hit the walls of a container or each other, they're going to conserve their energy. Their energy is going to stay the same. So if you were to drop a gas as a ball, it would bounce back up to the same height and then fall and then bounce back up to the same height and then fall and then bounce back up to the same height and then fall. So their energy is conserved when they collide into each other and to other things. And that's called elastic collisions. In reality, there's some loss of energy, but it's so small that we don't really consider it in our calculations and our explanations of things, especially for gases. And the last part that's super important to understand is that the gases will have an energy that's proportional to their temperature in Kelvin. So in other words, the higher the temperature, the more energy there are in the gas particles. So if you double the temperature, you double the energy. If you triple the temperature, you triple the energy. And so these are the main assumptions of the kinetic molecular theory, where we view gases as ideal gases, even though they're technically not ideal gases. But they're close enough that these assumptions will work to make our understanding of gases a little bit easier, to simplify our calculations, and to allow us to understand the world. This is a great TED Talk that goes over the properties of gas using the kinetic molecular theory. I do want you to watch it because on the next slide, you'll notice that there's a video that shows the main assumptions of the kinetic molecular theory, or not a video, an image. And so I want you to be able to explain this image using the main 5 points over here. And you can read the points, try to label the image. But if you're not too sure how, watch this TED Talk because it will highlight the points that I just explained here in a little bit more detail. So again, ideal gases don't actually exist. They're hypothetical gases. And we define them as essentially gases that have no mass, or that have a mass but no volume. So they're point masses, and there's no forces of attraction between them. And then they obey, like I said, those main points of the kinetic molecular theory. In reality, real gases exist, the ones we deal with every day, but a lot of them are so close to that ideal behavior, we can just pretend like they do fit in that framework, and it makes our lives a lot easier, and we get some pretty good observations and explanations of those observations. Now, we can use ideal gases and kinetic molecular theory to understand real gases. There are some conditions where you can't, and it's rare that we get these conditions in grade 11 chemistry, in grade 12, in most labs that you study, that you're going to be studying in, you're going to have the right conditions to be able to assume this. But when your gas starts to liquefy and the particles come really close together, then we can't use the kinetic molecular theory. And that usually happens when you have really, 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 really high pressures and really low temperatures, because the particles essentially don't have a lot of energy anymore. They come so close together, they start to become liquids, and that's where we can't really use the kinetic molecular theory. But it's not really going to apply so much for us. We're going to assume that we can use it, and we're not really going to focus on the cases where we can't use it. This is a great video as well. I do want you to watch it because it will help you to understand the difference between an ideal gas and a real gas. It'll show you what the assumptions are for ideal gases and how that's different from real gases. So take a few minutes to watch that and to add it to your notes so you understand what we mean by ideal versus real. And so again, here you can see just a comparison of ideal gases versus real gases. So again, in ideal gases, they're hypothetical. We're going to use them to explain the behavior of gases that we deal with every day, but they're not real. So for example, we say that there's no attractive forces between the gas particles. There's no intermolecular forces, for example, that will hold the gas particles together. And in reality, That's not true. There are intermolecular forces there that help to hold gas particles together, but they are so small that for most gases we can kind of ignore them and say they're not there. Just forget about it. It'll make our calculations too complex, and it won't really affect our answers anyways. So do understand that this is an assumption made, but it's not 100% fact or real. It's just an assumption made to make our models a bit easier to explain. And so you'll see more of that in this video as you go over the ideal versus real gases. So you should be able to explain behavior of gases using the kinetic molecular theory. So when I ask you to explain an observation, for example, gases diffuse or spread out rapidly. So if I this is going to sound like a weird example, but if you've ever farted, essentially, if there's someone in the same room as you, well, you know that it's going to reach that person eventually, pretty quickly, right? So you wait a couple seconds, and someone goes, "Okay, who did that? That was rude." Well, you have gases spreading out pretty quickly. So can you explain that behavior of gas using the points of the kinetic molecular theory? So if we go back here, let's see what points really apply to that behavior that they spread out. So, I mean, you could maybe say that they move randomly in a straight line. That's a possibility, but I don't know if it's really the best explanation for why they spread out quickly. You might say their volume is negligible. Maybe you could use that, but I'm trying to tie it really to more the spreading out part. Like why are they moving away? The particles moving away from each other so quickly. Um, so maybe part of it might have to do with the gas molecules not attracting or repelling each other. So if there's no attractive forces holding them together, that's why they can spread out pretty quickly. If there were attractive forces, it might slow down how quickly they spread out. But because they don't have any attractive forces, they can spread out pretty quickly as a result of that. So that might be the best point to use there. So you can see here, no attractive or repulsive forces exist between the particles in a gas, and as a result, they're able to spread out much more rapidly. Whereas if they were a solid, solids don't spread out like that because the forces are so strong between the particles of a solid or a liquid as well that it keeps them together in one place. So if you're asked to explain the behavior of gas using kinetic molecular theory, go back to the main points of the kinetic molecular theory and see which one best explains it. Yes, theoretically, you can argue for any of them, but there's always sort of one or two that best explain that concept. So, for example, you might say you put a balloon out on a hot day and it expands. Well, why is that? Well, let's see. I mean, you could say it's because they randomly go in a straight line, but I don't know if that's the best explanation. I don't understand the connection if you say that. Volume of gases is negligible. Again, I don't quite see the connection there. Gas particles do not attract each other. Yeah, I can see that because they spread out and they're taking up more space. But why do they expand on a hot day outside compared to being inside? Well, let's take a look. I mean, it seems like if you put them outside on a hot day, they're probably getting more energy. And because they have more energy at a higher temperature, then they're moving faster and they're expanding. They're taking up more space as a result of that. So, this here plus this here might be the two best points to explain that observation. So go back to the kinetic molecular theory points and choose the ones that best explain the observation that we're trying to get you to explain. And if you don't know these points very well and you didn't quite understand my explanation, do watch the video here and be over here as well to understand what those different points mean. And so that is an explanation of the gases under the kinetic molecular theory. Let's go to our handout to fill in some blanks to make sure we understand the concepts that we just saw. And a lot of this is really conceptual, so you do need to kind of buckle down, read the terminology that you saw in the previous videos, listen to the terminology, and try to conceptualize and draw and sketch to really get the concepts. So the focus of this video was looking at the gases and their properties, and we saw that they take the shape and volume of their container, that they're highly compressible because they have low densities, that they flow very easily. In other words, they have very low viscosity. We saw that they mix very easily with other gases because there's so much space between them. They're miscible with other gases. And we also saw that they experience this random motion, where you have the vibrating in one spot, the rotational, and then the translational kind of all together. And there's a special name for the motion of gases called Brownian motions. It's kind of different than you would expect. And there's a video you can watch on that. And they also expand as temperatures increase. So we saw that. So when you increase the temperature of gases, they will expand and take up more space. And so we saw that, you could explain behavior of gases using particle theory of matter. But in this video, we saw that we use a different theory called the kinetic molecular theory, where we treat gases as being these ideal gases. And so I put a few videos of kinetic molecular theory and ideal gases that you can watch to get more details. But I want you to get that ideal gases aren't real. They're hypothetical. They're hypothetical gases. And essentially they obey this kinetic molecular theory, the main points there. And they're hypothetical because we say that the particles have a mass, but there's no volume, they're point masses. And there's also no forces of attraction or repulsion between them. In reality, that's not true. Gas particles do have a mass, there is a force of attraction between them, but we can make these assumptions. We can pretend like a lot of the gases we deal with are ideal, because if they do have a mass, if they do have a volume, it's in reality they do have a volume, but it's so small we can assume that the volume's not there. And then same thing with forces of attraction. There are forces of attraction between gas particles, but it's so small we can pretend they're not there, and it makes our understanding a little bit easier. It makes our calculations easier as well if we make those assumptions. The only time a real gas doesn't really follow the ideal gas rules or assumptions under the kinetic molecular theory is really when you're under really high pressures and really low temperatures, because the gas molecules will start to liquefy and come really close together, and then it just won't work. Your assumptions are just totally wrong in that case. But for the most part, when we talk about gas chemistry, especially in grade 11 and 12, and for a lot of your labs you do in university or wherever, or in the workplace, you're gonna focus on conditions where it does work out. And if you don't, you'll learn about what happens then. So essentially the 5 main assumptions of the kinetic molecular theory for gas particles is that they move randomly in a straight line. The volume of gases is negligible, meaning that the individual particles don't take up space. In reality, they do, but we're assuming they don't in the kinetic molecular theory. But we call them point masses. In other words, they're little points with masses, but they don't take up space. Gas molecules do not have any attractive or repulsive forces between them, so they don't attract or repel each other, which in reality there are attractive forces between them, but so small that we can essentially ignore them and say they don't have them. If gas particles collide, their total kinetic energy remains constant. So that's called elastic collisions, which means that when they bump into something, into each other, or into the walls of containers, they won't lose energy. They actually do lose a little bit of energy, but it's so small, we pretend they don't. So if you were to think of gas particles like a ball and you drop the ball, they'll basically just keep hitting the ground and bouncing up at the same height and essentially never stop moving. And then gases, their energy is proportional to the temperature in Kelvin. So essentially, as you increase the temperature, you increase the energy, and they're proportional. So if you double temperature, you double energy. If you triple temperature, you triple energy. And it has to be in Kelvin, though, not in degrees Celsius, because remember, degrees Celsius is more of a relative scale. And so I did say there were some videos that you could watch to compare a real gas to an ideal gas. Do watch those videos to make sure you understand the difference. It might even be a good idea to make a chart after you watch the video to compare ideal versus real, but understand that we are using the ideal gas assumptions in this unit. And then we did some practice problems where we explained the behavior of gases using the kinetic molecular theory. And so what we did is when we have a question like that, we go to the kinetic molecular theory, we look at the 5 points, and we see which points best explains that particular observation. You don't just state a random point, you state the one that can really explain, why do gases spread out so easily? Why are they moving away from each other and spreading out really quickly? Well, what explains that? Okay, well, it looks like to move away from each other, you don't want them to be able to attract each other very strongly. So it's probably this point here, point 3, that they do not attract or repel each other. And as a result, since there's no attractive or repulsive forces, they can spread out pretty quickly. And so that's what we saw in this particular video, explaining behavior of gas using the kinetic molecular theory and assuming they are ideal gases. We're going to see formulas in the next few lessons, and those formulas are basically going to treat gases as if they're ideal gases. And it works out, even though they're not really ideal gases, even though ideal gases are only hypothetical, these formulas apply to the gases we deal with in everyday life because we have the right conditions for that. And it just simplifies our understanding of the world and allows us to really understand real gases in more detail. So do make sure you understand the concepts so that way the formulas will make a little bit more sense to you as we move forward.